Hi everyone, and here I will be sharing the sample code that I've created for decision trees from scratch. So this is really a very difficult exercise, and it was only created so that those who are more adventurous and want to try out new things can try their hand at creating a decision tree, like how I've described it in the tutorial sessions. So without further ado, let me just go through the code that I've created, and I'll just run you through the code to show you how this decision tree is done. So first up, we do the imports. We import pandas as PD. Okay, pandas is used for data frames. Okay, so this will be used to sort the data into basically like this kind of stuff like Excel, like that, rows and columns. NumPy is used for array manipulation. So this one will be used later when we have NumPy arrays. Next up, we have from sklearn, we import the decision tree classifier. This really is just meant so that we can see what the sklearn side does and compare with it. We also import the tree from sklearn. Okay, this is to help us visualize the tree that was created by sklearn. And graphics is a visualization module as well. So let's just run this code. First up, I just use the same kind of data that was in the tutorial. Okay, so these are the three input variables, the binary ones, and Y is basically the target label. So we create a data frame and then we visualize it. Let's see how it is. So it looks like this. So the aim is given this tree, ABC, we need to predict what's Y. So first up, we just use this thing called drop to drop the column Y so that we get an ABC input variables for X. And for Y, it will just be this Y column. So let's do that. So you can see X is this one and Y is this one. So the input features and the labels are separated. And so with that, we can then use the sklearn decision tree. We use the entropy method, do the fits, okay, and then we can render the data and see how it is. So let's take a look. This one, DT. So we need to find where is DT in my, okay, it's loading. Let's see. There we go. Here it is. So it looks like this right now. So you can see that we split on C, X2 is C, and we split on B, okay, and then eventually we get a clean split with all entropy as 0. So let's see whether we can do this on our own, all right? Let's try to do this using our own class. So over here, we use the decision tree classifier class from sklearn. Now we do our own class called my decision tree. I mean, I can also name it the same thing, but I name it differently so we can see that this was really done from scratch. Okay, so there were a few students who actually did their own. Okay, they did halfway of the assignment. They just did with this binary data set. Okay, and they also didn't really do everything. Like the prediction part was not there, but I'm quite happy that actually most of these things were already done. Okay, so let me just describe to you what I'm going to do. So first, the init. Okay, we do have this max depth equals to 2, which will tell us it's the same as this, which will tell us how many branches, how deep are the branches that we want. We have this thing called numbins, and this numbins is really just to tell us what is the number of splits of a variable. So let's say my variable is like a continuous variable from 0 to 10. Okay, so my numbins, I will then split evenly like 0, 1, 2, 3, so on until 10. Actually, in this case, let's say my variable is from 1 to 10. So yes, I will split this into 10 different bins, like 1 to 10, and then I can use that as a decision criteria for my decision tree. So these numbins can be, of course, increase if you want to, but you will just incur more runtime because you need to evaluate for more branches. So next up, we have this self.split. So I just created this in order to do the recursive splits. So we need a way to store, okay, if you go to the left branch, what do you do next? You go to the right branch, what do you do next? So using some form of method, using a list to actually describe what will happen after each split. Okay, we'll see how this is done later. So first up, we need to mimic the fit function that we see in sklearn earlier, this fit function. So just take note, when you do a class, you need to define everything here with self, okay, so that you can later on do stuff like clf.fit. Okay, so you do the self function, you can actually call yourself and then call this function. So that's the purpose of the word self here for the function. Okay, so we fit x and y. So if x and y are not data frames already, we make this a data frame. All right, this so that it can be compatible with like list or arrays as well. Okay, then we have this thing called the default class, which basically is the majority class. So y.mode tells us the majority. So I can just show you. So what's y is like that. Y.mode will tell you what is the majority values. And then when we take dot values, we will get the array of it, and we can just take the first one. All right, so that's exactly what we do here. And also, we can also use the y, okay, dot value counts in order to like find out how many of each number there are. Later, I use this a few times at the bottom, where we use the value counts to we use the value counts here in order to calculate the entropy. Okay, because over here we can get the counts of all the objects. All right, so first up, after we get this default majority class, so this is basically if let's say the node is unlabeled, or that means like the node has no branch there. Like basically, sometimes your decision tree you have end up with a leaf node with nothing. In such cases, which is quite rare, in such cases we just use the majority class. Okay, but this is typically not used. I just use this as a fallback just in case we need a sample class in case of no values of your y's. Okay, then we do a split. Okay, this is using this method called recursion. Okay, so this is typically used in competitive programming. But the idea is that you take, like, for example, you take one tree like that, you split into two branches. Okay, like decision tree is split into two branches. Then you have two different pathways, right? So actually the way that you split here, this method, this original method, it can be actually superimposed into here as well. So you can actually call a recursive function and then you can split this into two parts as well. So if we define a recursive function, we can just keep doing this to the next section in order to generate like sub branches. And then from the sub branch, we can also call the functions on the sub branch in order to generate even more sub branches. So all these are quite useful techniques. Okay, and this is used to create a decision tree. So first up, for the first call of my recursive function, I call the original x, original y after making the data frame, and I put my depth as 0. Okay, so that basically will keep track how deep we are in the decision tree. And once we reach the max depth, you should just terminate and then not split anymore. Okay, so what does this tree recurse function do? So firstly, if there's no y, length y, basically if we split into two branches and that branch has no samples, okay, then we just return the default class as the label, right? But if the mode is pure, that means like there's only one of like class 1 or class 0. That's why the value counts is the length is just 1. Then we just return whatever that is the class of this pure node. So if it's like this node is all class 0, then we return class 0. The node class 1, then we return class 1. So this actually helps to do it because the mode tells you the majority class. Okay, same thing if we have reached the end of the depth, we just return the majority class here. Okay, this is just to make sure that we can classify more samples correctly. Okay, then now we have a list of variables. So the variables, if we see here, this is list x.columns. Let me just show you what this does, x.columns. So it's just like giving all the index for this. And then when we do this, we can actually see that we can print out all the variables here. So we can see all these variables here. Later we'll look through this. These are just like the entropy. What is the entropy? The lower the better for your child node. Okay, because remember information gain is entropy of parent minus average entropy of children. Okay, since the parent is going to be the same for that branch, okay, it's just basically we are just going to take the average entropy of the children, okay, in order to get our entropy. So the lower this entropy value here, the better the information gain. So we start with a high number for best entropy and we go downwards. We want to get the lowest value for entropy. Okay, then we have all this best x, A, XB, YA, YB will be the X and Y values for the two child branches after we split. Okay, so what we do is we look through all the variables. We look through all the possible uniform bins, okay, based on the number of bins. That's why we have bins here. Okay, num_bins is 10, works pretty well already. Okay, then basically we split into two childs. One child is where it's below equals to that value. The other child is where it's greater that value. Then we split the X and Y accordingly. Okay, to calculate the entropy, we just take the proportion of samples in child A, okay, times the child's entropy plus the proportion of samples in child B, in node B, times the entropy. So this is the average entropy, okay. And then if this entropy is smaller than the best entropy so far, smaller equals to best entropy so far, we update the best values for everything, okay, so that we can use this for the recursive loop. Okay, then what we do here, this is the very interesting part. Okay, this one is basically saying that we split everything into these three formats. Okay, the first one will tell you what is the best split, best value, best entropy in the form of a tuple. And then after that, we have the outcome for child A and the outcome for child B. Okay, which is basically we do the recursive function again. So we do the recursive function here and the recursive function here. Notice that we make a depth plus 1 over here. This is important because as we go down the next layer, we want the depth to increase until we reach the depth of the next depth. Then we'll break out of the recursion, right? So then with a recursive format, we can see that this is going to be filled more and more. And eventually, if there's no need to recurse anymore, it will just return the label, all right? So later you see how we actually use this to predict. Okay, so I'll go through the entropy function now because we talked about the entropy here. So the entropy function, if you look all the way down here, the entropy is just basically taking the sum of all the different classes, okay, based on the value counts, which tells you how many of each class there are. Okay, then we divide it by the total number of classes to get a proportion, okay, to get a probability or the proportion. And then basically we just apply the entropy formula, negative sum of pi log 2 pi. Okay, and over here I did this. Okay, so if your pi is actually 0, okay, log 2 0 actually gives you negative infinity. Okay, so you don't want that. Okay, you want to just make this 0 instead. Okay, this is just for number stability. If not, you'll get not a number here if you have pi equals 0. So just take note of this. Okay, so now we also have this thing called the predict function. So the predict function is basically given okay, so the input is not label X, the inputs is the features X, okay, and output is the predicted Y. Okay, and so for this predict, firstly, if it's not a data frame, again, make it a data frame. And over here, what we do is we basically, because when we do the prediction, we sort of have to do for each single element ourselves. If we don't do for each single element ourselves, so it's actually quite hard to actually go through because X can have like multiple samples. Yeah. So for each sample, you have to go through different parts of the decision tree. So you need to sort of look through individually and then you combine the predictions again later into an array. Right. So this is what it's doing. So we just look through for each of the samples. We do this recursive prediction function. Okay. I mean, there's also a way to do this all together. Okay, but you need a vector to tell what is the current split value. Okay, so this is something more tricky and I decided not to implement it. We just do the basic one. So how do we do this recurse predict function? So to start off, this self.split, remember, is okay, so I can show you roughly what the self.split is. Okay, let me just run this. Okay, if we were to do the decision tree max step 2, you see that it first splits on C, then it splits on B. Okay, and eventually the entropy is 0. Okay, so you can see over here, split on C, then split on B. So this one will be class 0, class 1, class 1, class 0. So you can see over here, class 0, class 1, then class 1, class 0. So it's actually quite cool because this is the split. Okay, and then the next element of the list will tell you what will happen on the left branch. And the next element will tell you what will happen on the right branch. Okay, and then after that, you can just, if let's say you are going to the left branch, you can take a look at this. So it's again in 3 parts. This part here on the left will tell you what's the decision boundary? Okay, like this one is B smaller equals to 0. It's actually over here. B smaller equals to value. So B smaller equals to 0.88888. Then you go to this left branch, which is array 0. If not, you go to the right branch, array 1. So this means it's class 0 and class 1. So once you reach here, you realize that this is no longer a tuple or a list. Okay, this will then be the class. You can return the class. So if let's say I were to do the decision tree iteration, I can just go through here. First, I see, my C is actually 0.5. So I should go, so if let's say C is 0.5, child A is C smaller equals to 0.888. So I should go to this branch. Then I see, my B is actually 0.9. Okay, so actually 0.9 is bigger than this value. So I should look at this branch. So hence my data with a C of 0.5 and B of 0.9 should be classified as label 1. Okay, so that's how we do it. Okay, so back to this recursive predict function. How do we do this recursive prediction function? Basically, it's the same thing here. If the type is not a tuple or list, then we return the split, which is basically return this label itself. Okay, if not, we can take this split. Okay, this is the split. Okay, in the first case, the first time we do the split is here. We can then do split info B1, B2. So split info is like the split info is this one. The split info will be so split for the first time round, split will be all like that. Split info will be like how to split the branch by. And then B1 is branch 1, or the left children, and B2 is the right children. So we can actually split this up here. And then from the split info, we can split into the variable and the value and the entropy. We will not use the entropy for the split, but it's just there for information. Okay, then after that, what we do is we will take the next split. The next split will become B1 if it's smaller equals to value. If not, it becomes B2. Then what we do is we will return the recursive prediction again of this variable X plus the next split, which is the subsplit here. Then we apply the same thing again. Okay, so this one will become the split info, and then this one will be a B1 and B2. So in this case, we will get something like B1. Okay, and since this B1 is no longer a tuple or list, okay, we will then just return this array 0, which is the label. So that's how this prediction function works. Pretty cool. So in the end, we can just predict like X. Over here, you can see we get 0, 0, 0, 1, 1, 1. So exactly what we expect over here, 0, 0, 0, 1, 1, 1. Right, so how does this looks good, okay, to do on the binary input and binary features. Let us see how good this is on the Wisconsin breast cancer dataset. Okay, so let us basically go on. Let's just see how good this is on the Wisconsin dataset. So over here, I just use the load breast cancer. Okay, this is basically a shorthand way to load the data without using the CSV file. All right, because actually sklearn already has the Wisconsin breast cancer dataset here. So we can load the data into X and Y, the data and the target. So we can take a look at how the data is. So we can see like X here, this will tell you the 30 features here, and 5, 6, 9 different observations, and Y is the label. Okay, so let's run it on sklearn using a train test split of 0.5, random state of 42. Let us see how they classify this. Okay, and at the same time, I also import the accuracy score, precision score, and recall score just to see how good this is. So let's just print it out. Yeah, it's not bad, 94, 95. Let's see how they did it. Okay, BT, WD, BC. So you can see that they split on 27, they split on 23, then 4. So overall, the entropy is like 0.5, 0.2. Not too bad. Okay, let us see how ours works out. I'm just going to run all of them. So you can see that ours split on 27, then splits on 22. Okay, so you see split on 27, then okay, here is slightly different, but not a big deal. Okay, because the entropy, let's see, this is about 0.59. Entropy, we get about 0.36, is around there. Okay, so maybe the way that we split, because of our bins, we only have 10 bins, is slightly lesser than the sklearn one. Okay, but it looks like it's able to split pretty well. And actually, based on my tinkering with this, I found that the sklearn actually uses a non-greedy split. Okay, so actually I think they really just expand out the entire decision tree and then find the best entropy of the children all the way at the child node. So they really expand all the way down here and find out the children. Okay, so this is something that we didn't code because it might take longer to run. Okay, but definitely you can make this non-greedy, and then you can do a recursion to find out what is the best way to split all the way down to the child node. Okay, so maybe they only did a one-step look ahead because I think you do too many, it's not feasible. Okay, so let's take a look at our recall accuracy is slightly lower, precision slightly lower, recall slightly higher. So I would say it's pretty similar. Okay, the reason why it probably varied is that it probably did a non-greedy split, and also maybe they use more bins. Yeah, maybe we can just do like num bins equals to 30 and see whether it helps to improve the split. So we split into more finer categorization, and indeed, see, we did better than sklearn already. 95 accuracy, 96 precision, and 95 recall. So actually, this is not bad. Just doing this. So here's 27, 23, and 16. 27, 23. Yep. And this one we got 16. So actually, we did a better thing. So over here, you can see that if I were to just change the num bins, or maybe I just change the features, the input number, sorry, the samples, the kind of samples I gave it, you can see that actually the accuracy, precision, and recall will be affected quite a bit. Okay, then that's why methods like random forest, where you use an aggregation of like decision trees with different input features, can work so well because they each look at different aspects of the data. It prevents overfitting by basically combining like the majority vote of expert predictions that look at different parts of the data. So that's quite interesting. You can see that like if we use sklearn decision tree and we use ours, I think we combine the model outputs and then like maybe we do majority voting, it will probably be more will probably be more accurate and less variance. Okay, less variance than if we had just like did only one decision tree. So yeah, verdict is that it's pretty similar, and sklearn does not seem to be doing a greedy split. Yeah, and I hope this was interesting for people to try out to do this bonus question. I think this wasn't easy because I myself took about 3 hours to code this out from scratch myself. You can see that there's quite a lot of recursion involved here. So this is definitely not beginner friendly. But you know, everything starts small. You can do parts of it. Some groups just did parts of this DIY decision tree. And I think the main thing is really just to experiment. You won't know until you try. And sometimes if you think that something is too daunting, you just give up straight away. I think then you miss out quite a lot of learning opportunities. So my motto is really, if you can like see a very difficult problem that you're interested in, you can try to break it down into smaller steps, like maybe just code the entropy first, then code a non-recursive function first, then followed by the recursion. And then you keep doing that, you can actually probably learn something very, very difficult just from the fundamentals. Yeah. So yeah, all the best for people who are trying to code out. Okay, so this is the end for this bonus question. And I hope you enjoyed looking at how we actually coded this out. All right, thanks and see ya.